Okay, then we'll have a.
I did it all.
Right. Enough to remember that Alma was strongly sold to the community that Alma would literally make pictures like this, where you'd see, in fact, almost all the Alma predictions, or that you could see these nice arcs, and you'd see the planets actually accreting. Alma has definitely delivered the most spectacular images of disks, and you can see these huge cavities. It's a little rare that you see streamers spiraling around individual planets, and you know, maybe in the case of PDS-70C and possibly B, that's an exception, but for the most part, it's been elusive. But what we have been able to see are these beautiful disks with these beautiful cavities. And what I'm showing you here are some of the bigger cavities. All these cavities are scaled more or less correctly. Mostly borrowed from Miriam's beautiful paper with Francis Logan. And what you can see here is that these red dots represent H-alpha bright objects that we've been able to find. And in the smaller disks, we have not been able to find glowing H-alpha objects. In this case, it's a star. In this case, it might be a planet, it may not, but we're following that up right now. And PDS-70 is the best case, where we've got PDS-70C here and PDS-70B here. This is what the disk looks like in scattered light. All right, so you can see that it's you know, inclined in that direction. And here's again another scattered light image. So this is done with adaptive optics, and this is sub-millimeter continuum. And what we're basically seeing here is that these objects are kind of near the forescattered side, the side that's closest to our line of sight. Now, a little bit of theory is probably good at this point, even though I think you're all following along. But the idea is basically, and Sally Dobson-Robinson had a very nice paper that just sort of showed that, you know, these large cavities are kind of hard to keep dust free, because dust keeps wanting to fall in from the outer edges. And one of the ways of keeping these really large cavities, and they're quite large, you know, we're talking about 20 to 70 astronomical units. So our entire solar system could fit inside these cavities that Alma's seeing. So how do we keep them dust free? Well, one way you can do it is by having multiple massive planets. And if you put like three, in this case, there's 3 massive planets that have been injected into the simulation. You can see over time, they open up one of these large cavities. Now, because gas and dust are streaming continuously into the cavity, and we know this because the star is still enjoying the gas falling onto it, and we can see H-alpha coming from the star, it should also be the case, I thought, that you should be seeing H-alpha coming from the individual planets themselves as the hydrogen gas falls onto the individual planets that are clearing the cavity. In other words, if you see a big cavity, point your visible extreme AO system at it, put in an H-alpha filter, and just go look. And then you might want to also image in continuum. In continuum, you should see this. In H-alpha, you should see this. All right, really simple kind of experiment. All right, unfortunately, the diffraction limited large telescope H-alpha AO system took about like 20 years to build. So, and we first were able to do this science with the adaptive secondary, the 400 element MagAO system, which I was the PI of, and Jared helped a lot with that. And now we're using MagAO-X, which is Jared's instrument, which I helped him build. And here you can see a nice example of what it looks like on the platform. So this is on the Naismith platform. This is what it looks like without any dust covers. Of course, we very rarely take all our dust covers off when we're in the dusty telescope, right? So this is just a CAD image, but it kind of sets the scale. It's a 6.5 meter telescope. For those of you who don't know Magellan, well, you should all know Magellan. You know, it's Arizona's like thing, you know. And thank you, Buell, for continuing to be part of Magellan, because it's an amazing telescope. It's an amazing site. It's really, for somebody who's worked in Mauna Kea, worked at Paranal, and worked in Chile, I can say with some confidence that really, and done AO at all sites, and they're all good sites. Well, anyways, Paranal is not quite as good as these two sites, but it's very dark and it's very dry. So it wins on those things, but Las Campanas, where Magellan is an exceptionally good site where you can get 0.5 arc-second seeing all night long for the entire night. And that's very exciting. And I'm going to show you what we can do with that sort of capability. I should also mention, it's nice that we have Naismith platforms because that means the instrument is gravity invariant. And in fact, one of the things I'm most proud of with MagAO-X is that we went through some work to make it floating. So it's a very rare example of an instrument that actually just floats. There's no connection between it and the telescope. So if the telescope's vibrating, which it does, and if there's wind and the telescope's vibrating and all of that, MagAO-X doesn't care. It just sits there floating on its floating cushion of air. And so that eliminates the really high frequency vibrations that limit so many other AO systems from being able to work at these frequencies. And of course, I'm talking about a very complicated instrument that takes a very talented team to run. And in particular, I'm going to call out Jared here. And this is actually the group photo that was taken the night of where I was showing you most of the data that was taken. Obviously not everyone in the MagAO-X team is in this photo, Maggie, Wiles. But anyways, most of you are, and cool. And anyways, it's a big group and we do a lot of stuff. But I want to show you some of the really exciting science that we're doing now. This is what it looks like in the clean room in Chile just before it goes up and mounts on the telescope. It's very complicated. There's basically, it has 8 off-axis parabolic mirrors for a 4-pupil relay. It has advanced chronographs. It has a Woofer-Tweeter 2000 element deformable mirror, but it also has something that's really unique in the world of science is it's got this last deformable mirror, which itself is a 1000 element mirror. And the only thing that mirror does is take care of non-common path aberrations. And for those of you that are really into AO, you know that almost all of AO science is limited, especially high contrast science, is limited by the non-common path aberrations. We do all this work to build these beautiful AO systems, and then we feed it with like half a wave of focus or astigmatism or spherical, and it's just sort of sad. And you can kind of tune it out, but it's difficult. What we do here, instead of detuning the main AO system, we just tune up this one last mirror so that it exactly nulls out any of the non-common path aberrations that we find at the beginning of the night. And then because the system is so stable and so stiff and there's no gravity and the temperature barely changes at the site, that we can hold those non-common path aberration corrections for many hours. And in fact, in this case, like all night long. So it's a remarkable piece of technology. Here's a movie by Jay, who's just, I don't know. I mean, yes, it's an Alt-Az telescope, and this is what it looks like when it opens, but I still think the time-lapse movie is kind of fun. You can see there's MagAO-X mounted there, and you can see it really doesn't get shaken around much as things move around because it's on that nice Naismith platform. Now, here's a movie that's actually really exciting. This is my favorite movie in the whole world. It just shows the AO off, and now the AO's on. And if it looks pretty much like magic, that's because it pretty much is. It's a remarkable thing for someone that's been doing AO on and AO off movies their whole lives. You never see performance like this. And this is because, of course, we're in the visible. So if you don't have AO on in the visible, it really does look pretty awful. Although I think that's a half arc second seeing star. So it's actually, most people would be very happy with that image. But when we turn on the AO, it goes all the way down. I think this is in the Z prime band. Well, it's 875 nanometers. So it goes down to about 28 nanometers, 28 milliarc seconds. So we're going from about 500 milliarc seconds to 28 milliarc seconds. And that's just hugely enabling for the science. Maybe I'll just play that one more time. And obviously it's a binary star, okay? And when I turn the AO on, all right, you can see the companion. When the AO is off, you absolutely cannot see the companion. The question that everyone asks is, oh, what about all these other companions? Okay, so these are well-known primary and secondary, first order, second order diffraction from the grid that is our deformable mirror. We have 2,000 elements on a single mirror that's only 18 millimeters across. And of course, that makes a grid, and the grid will diffract. And we know where the spots are. It doesn't bother us. We let the sky rotate. And so things that are real will rotate on the sky. The only thing that will rotate on the sky is just this little guy. All these little spots will stay exactly still. And then through principal component analysis, things like pi clip, we can remove all those substructures. And so we can do very, very, very high contrast imaging with this setup. Okay, and this is just a deep exposure, what the PSF looks like at a wider Z band. What you can see here is the dark control region, because we're actually removing light there with our deformable mirror. And that's kind of and of course you can see spider arms and, and obviously a diffraction limited central object. And this is a picture that Jared published a while back, just to show that we're making really high Strel images in the visible. Again, because, I spent a lot of time with Maggie and Alex aligning all of this optics. It was like a big deal. I can't help but just to show one picture, but of course it's maybe too complicated to understand, but it is a complex chronographic relay with a bunch of guide cameras. But long story short, light comes in here, all right, and some of the light gets sent to the pyramid wavefront sensor. It gets split here, all right, and then the science path is this kind of blue light, right? Because we're working in the blue, and we send the redder light, in this particular case, to the wavefront sensor. This is the way that we split the light up for the H alpha, but every H alpha photon gets sent along this blue beam, all right? And then that H alpha photon, a few bounces, and it basically finds its way to this beam splitter cube. And then the H alpha photons go to that camera, and all of them. And then we also simultaneously, and this is the important part, we simultaneously image off of H alpha. So we do continuum imaging over 8 nanometers, and then H alpha imaging over a beautiful custom, it says 8 nanometer here. That should say 1 nanometer, 1 nanometer H alpha filter, so a beautiful custom made. So we do narrowband H alpha, but we're also monitoring continuum at the same time, exactly the same time. So we have exactly the same PSF. So we can subtract one from the other, and the only thing that will survive that is something that has actual H alpha and emission. All right, and that's the idea. Okay, so how do we do? Well, we do pretty well. This is a good test piece, is PDS-70 B and C. PDS-70b was the first exoplanet that was discovered to have H alpha with MagAO, and here we're looking at it with MagAO-X. We're comparing to HSD. MagAO-X is on a 6.5 meter. HSD is 2.4 meter. So we can outperform HST, no shade on HST. It's an amazing telescope, but we're just 3 times bigger. And you can kind of see that, the planets are a little bit more puffed out and stuff. And this is Yifan Zhu, who was also a grad student here, who is awesome. And he's been doing this sort of same science with HSD. HSD doesn't need a guide star, so it can look at fainter things. But unfortunately, it's a smaller telescope and gets more limited by diffraction. For us, it's pretty easy to see like the companion. It was difficult for HST. And and we've been looking at PDS-70b and C. So this is a star. This is one of the more important stars in the sky. It has 2 planets, both of them accreting H alpha. The second planet was discovered to be accreting H alpha by Sebastian Haffert, who was a Sagan postdoc or Hubble postdoc here. And he still works with the MagAO-X crew. So this was discovered, and this was Kevin Wagner was working with us with MagAO, discovered B at H alpha. Sebastian discovered C. There's strong connections between Steward and H alpha imaging of exoplanets. What you can see here, though, is MagAO-X, looking at it over the years. And you can see we're getting better. In 2022, we're just kind of starting. There were some teething pains. We didn't have that beautiful 1,000 element non-common path deformable mirror. So the images are not as good. You can sort of see the planets if you squint. And you can see the PSF's not so great. But then we move forward, and we're in 2023, and we're actually getting some pretty nice images. We're using that narrowband H alpha filter. We're using the 1K non-common path DM. Things are really looking up. And then here we're figuring out a better way of tuning the 1K on sky using phase diversity. And that's actually producing even better PSFs and really nice results. And in fact, as you can see, this was a shorter exposure than this, but it still wound up looking very good in terms of contrast. And you actually almost never see this you can, I know all these high contrast imaging papers, you will almost never see the PSF shown in the high contrast imaging paper. It's like the people go out of their way to hide what the PSF was. They will not report Strel, they will not report full width half max. They will just say, we downloaded this from the archive, and this is what the pipeline spat out. And okay, that's fine. That is one way to do science, but I think it's really beautiful to be able to compare the PSF with the science. So because the PSF is the only thing that really matters in high contrast imaging. And here we've done a very meticulous job of measuring the Strel. Again, this is Strel at 26%. You might be thinking, oh, well, that sounds crappy. But it's on a 6.5 meter at H alpha. And that is actually extremely hard to achieve, right? I mean, you might be like, well, what about Webb? Webb's like almost 100%. Well, and it's the same size. That's true. But Webb doesn't work at H alpha, obviously. Webb doesn't even work in the visible. So we're still making images that are about 3 times or so better than the very best, maybe factor of 2 better than what Webb can do. It's very, very bluish, although it's not really meant to work there at all anyways. So again, this is not really what you can do on Webb. You can't do this on HST at this sort of, because HST is just too small. So there we go. And all right, so moving on. All right, so let's take a look at, so one of the things we've been able to do is we've been able to find disks of CPDs, some scattered light around the individual components. And this is real data, and there's B and there's C, and you can kind of see that there's some scattered light. Now, granted, there's scattered light coming from the star too. I want to have some more follow-up on this, but we have been seeing these things continuously showing up. And so the idea is kind of like maybe we're seeing a little bit of force scattering from the star off of the CPDs around the individual planets shown by these red dots. And so this is kind of like an artist's illustration. Actually, the artist is my daughter, Emmeline, because like this is the best talent I could afford. And although actually Emmeline's pretty talented, so she did a nice job there. Here's just a simple little movie just to kind of show what I'm trying to get at here. So the idea here is that this is the data, and then what I'm going to do here is I'm just going to fade into the artist illustration, and that's kind of approximation of what might be going on in the PDS-70 system. All right, and then what I want to show you here is that they're changing in brightness over time. So this was a new discovery, is that you should see C getting brighter. You can see them orbiting the star, obviously. You can see that C is actually getting brighter, and B is actually getting a little bit dimmer. So it's pretty bright there, but it gets quite a bit. B drops dramatically, and whereas C gets brighter, and they actually flip. So you start off with B being brighter, but then 3 years later, C is brighter. And that may seem like, okay, well, it's H alpha accretion. Nature's kind of variable, but up until now, we really hadn't seen really good evidence of that. Yifan published like about a month after me an HST survey that suggested something very similar. So we're in agreement on that. So yes, H alpha is variable on planets. CPDs seem to exist around these things, and that's sort of obvious. And so, really the 2 takeaways for the first part of the talk is that in the PDS-70 system, B and C are both variable, and they both seem to have dust, very, very compact, like 30 milliarcsecond radius dust rings around them for CPDs. I think that's exciting. And I should also mention, of course, that ALMA has seen CPDs around certainly C, and there's evidence too that there's material around B, but it's a little bit trickier to pull out. So this is not earth-shattering, but it's the first time it's been seen in scattered light. So that's exciting. And I should also point out, now we're going to talk about new things. And
so then you know it's scattered because you have photometry, or
well, okay, it's scattered because it's at H alpha, and well, actually, this is in the continuum band. It couldn't be thermal because we're working at like 668, and so it's not thermal. It's extended. It's not point-like. And so it pretty much has to be scattered. We do now have a polarimeter, though, at MagAO-X. So I'm not going to talk about that today, but Miles is literally here as our new Bach fellow, our new brass fellow to basically exploit the polarimeter. And so that actually is exactly what I want to do. So you've anticipated exactly the next step. is to try to do polarimetry, which should make those things actually show up better. Because right now I'm competing with all the starlight. If I could just focus on the polarized light, then they should really pop out nicely. Jolin has used MagAO-X to make a major discovery where we've discovered a brand new planet. I'm just going to call it 2-mass 1612b, but you can see the full thing. Sometimes we also call it Maxprotoplanet 1b. I'm not going to go into too much detail about this because Jolin's just had her AppJ letter published, and I think it's accepted. It's on AstroPH, and you can see it's the same sort of thing. In continuum, you don't see a planet. At H alpha, you do see a planet. And then if you subtract continuum from H alpha, you can, of course, still see the planet. And so she should give her own thing and talk more about this very exciting discovery. But it's the same sort of idea where you've got a massive planet inside a large Elmer ring. Now, I want to spend the last part of the talk talking about this absolutely amazing disk that was discovered by Rachel van Cavelin at Leiden Observatory. And she's a graduate student that's been doing this survey with Sphere to look for planets around young stars. And this star, WISPIT 2, otherwise known, it just basically had a Tycho number and had no papers published about it. It's getting to be kind of rare, but there are still these little treasures waiting to be found in the universe by people in this room. This star had literally no papers written about it ever. It was just completely ignored. However, Gaia, being the amazing machine that Gaia is, saw that it had space motions that said that it could be young, and people were sort of interested in looking at it. Now, fascinatingly, IRAS actually, way back when, like 70s, 60s, I forget when IRAS published its papers before my time, but my advisor's advisor, Frank Lowe, was heavily involved with the project. And anyways,
1980s, don't make that.
yeah, it was 80s, something like that. And so IRAS found this disk. And shame on our whole community for then never looking at it again. It cataloged it as a faint galaxy, but still, And then ROSAT found it, and then some people looked at it, and because of course it wasn't, well, they were excited because if ROSAT finds a galaxy, then it could be quite active for star formation, et cetera. But of course, it was actually ROSAT was detecting X-rays from the young star. And people looked at it and said, there's no galaxy there. And again, it was just ignored. Rachel was able to look at some sphere data. They did this wide survey. It's also in Aquila. And for those of us that do young stars, it's like, we don't think a lot about Aquila. We think of Upper SCO and things like that, but Aquila is adjacent to, obviously the Aquila Rift. And there's a lot of star formation near there, but not actually so much. So it's not like in a well-known young group, although there is a group that it might be related to. Although it's but there's, as I say, that's the amazing thing about things like Gaia, you find new things. Anyway, so this is this amazing ring system. And you can see it has at least 4 rings and probably at least 3 gaps in a cavity. All right, so now when we, I was asked to just follow this up. Sebastian, was like, oh, we should look at this. This is very exciting. And so we did. And as you can see here, it was fairly obvious that there was an H alpha bright planet sitting in the gap. And, you build an instrument, you have a certain science goal in mind, you tease out these things, signal the noise of sort of 5, and you're like, okay, yeah, we're doing science, blah, blah, blah. But when something like this happens and you get a signal noise of 12, it's just so rewarding. It's just like, I knew right away, this is the second night. This is the second night after the really discovery night. The discovery night was closer to maybe a signal noise of 6. But I knew like, oh yes, this is exactly what we're looking for. And what was really cool is that the position of the planet, as you can see, this is an H alpha image. The planet was right in that main dark ring. So it's in a gap. And that was actually, even though it's supposed to be the case that planets are carving these gaps, it had never really been clearly seen as a direct image before. And so certainly never before seen for an H-alpha planet, an actual accreting planet, accreting material and clearing a dust-free gap. So that's really important for planet formation theories. And this is the main data that I took for the paper, and it was just done in April. So, just a few months ago. And so the main thing to take away from this is that if you look in continuum, you don't see anything. Okay, so that's important. All right, otherwise it could be a star. All right, and then you look at H-alpha, these are the discovery images, and you can see something there that, for me, I was like, I fell off my chair. I was so excited about how strong that is. I was just so excited, and I just smiled for a whole 24 hours. And then anyways, and then this is what it looks like. Of course, if you subtract off the continuum, it still looks, sort of the same. But then, the brilliance of reducing your data as soon as you take it is that you find something interesting, and then you can kind of, hopefully, you've got some more time before the run ends. And I did have some more time. I had this amazing night, April 16th. And on April 16th, I was able to image it again. And I decided to do something a little different. I wanted to do Z prime, like a broad continuum filter and H-alpha. And you can see the seeing was much better than the previous night. And we got about 25% more rotation. That helped. And we just nailed it. I mean, it's just beautiful. And as you can see, it's a 12 sigma detection. You might be able to convince yourself that there's something there at Z prime. That took quite a bit of data reduction. That's only that's 10 to the minus, that's about 300,000 times fainter than the central star. Okay, that's how faint this planet is at Z prime. So it's a very high contrast image. It's about 310 milliarc seconds, so 0.3 arc seconds, which for us is really wide. So for us, we consider that a wide companion. 300 milliarc seconds is easy for MagAO-X in the visible, but even still, 300,000 times fainter is faint, right? We're actually starting to approach reflected light brightnesses of extrasolar planets. And so that's exciting, although that's not what this observation was about at all. This is thermal light that you're seeing, if you believe it's real at all, and I'm fine with that. This is only like a signal to noise of 2, so I'm not gonna get too excited about that. However, this I will, I'm super confident in because it's a signal to noise of 12. Okay, and then yes, sure.
This isn't the first H-alpha detection. This is the first H-alpha detection of a planet that's also associated with a gap.
That's exactly right. That's exactly the right way to parse it. You can see here, there's the edge, and then ring 2, you can see it here, and there's a planet right in between the two. And you might be thinking, because every artist illustration with a gap, you always see a planet in there, and this is kind of like, oh gosh, it's Puck, I think, in the inky ring of Saturn. You can see this in Saturn's rings too. You see these gaps in Saturn's rings. You see moons right in the center of the gap. Right? I mean, this is something that nature does, but we've never been able to directly take an image of a planet in a gap like this. And we've never been able to see H-alpha coming from a planet in a gap, even though it should happen. But I think there's a mass limit. I mean, this guy's about 5 Jupiter masses, and we know this because we took this beautiful image, director's discretionary time. Thank you, Joe, at the LBT, reduced by Gabe, and who's a graduate student working with Kevin Wagner. And so Kevin and Gabe were great with this. They really did all the work. And you can see this beautiful image from the LBT. And, it's kind of extraordinary because it's just really just a beautiful image. And this is at L prime. So this is a thermal image. And again, you see that, because this thing at 5 Jupiter should be about 1200 Kelvin, at L band, it just pops right out. And it's just beautiful. And you can also see that there's another inner companion as well, which we call CC1. I'm going to talk a little bit more about that. But it's a beautiful thing where we found something exciting, reduced the data, thought it really looked great, and then we're able to get time on the LBT. It's exactly the sort of thing that Stewart's built to do. And this is such a beautiful object because it's right between the north and the south. So every telescope in the world can see this object. And so that was kind of nice too, because sometimes they're far to the south or sometimes they're too far to the north. And this one's at -7 degrees deck, so it's pretty easy. Here's CC1 at a whole bunch of different wavelengths. We don't see H alpha from it, which is too bad because that would have been nice. But we do detect it quite brightly at Z prime. Whereas I was just talking before, the WISPIT 2b is almost undetectable at Z prime, but it actually is quite a bit brighter. So that right away suggests it's hotter, which probably means it's more massive. And then here we are. This is ExAO. This is so my friends at Leiden were pushing along, and they were getting director's discretionary time at ExAO, and they got some nice sphere images at KS and H. And this is the KS image where we could see also thermal light from CC1. But there's a chronograph in here, and the chronograph is blocking a lot of light, so it doesn't come out too well. The real winner is actually the non-chronographic image from LBT using the LBTI LMIRcam camera. So even though it says LBTI, we were just using one side of the LBT for this reduction, and you can see it's just really beautiful. How much thermal light is coming from that object. And that's kind of suggestive of maybe being something like 9 Jupiter masses. This is a crude attempt at a color image where I'm using the red as the LBT image, but this is a slightly better technique of using luminance RGB, which is my new astrophotography technique that I was taught by high school kids on how to actually make a pretty image. And those high school kids are amazing what they can do with their amateur telescopes. And anyways, here I'm using the luminance channel is pegged to the Z prime image. And just to walk you through it, I mean, basically here's the ring, okay? There's the inner cavity. There's the CC1, the 9 Jupiter mass planet at 14 AU. Here's WISPIT 2b, the hero, which has the H alpha, and it also has the thermal. And so here I peg blue to the H alpha and the thermal to red. And if you mix, I almost didn't know this, but if you mix blue and red, you get kind of purple. So it turned out to be kind of a purple planet. And so that's it. And then you can see it's in its gap, and then you can see the next ring. Of course, we have 5 milliarcsecond pixels, so our rings don't look as nice as other people's rings because we're way over resolving the rings. But even still, it's an extraordinary picture, really. It's just absolutely. I mean, I've been doing this sort of science forever, and I've never seen an exoplanet picture quite as pretty as this. To me, this just has everything. Multiple planets, rings, gaps, H alpha, and again, very high resolution. And here's a little cheat sheet for everything that is sort of on this image. So, and this image has also been picked up a little bit in the press as well. And there's also a really beautiful version of this that was made using just sphere data. So we did multiple. So I've been working with Rochelle and Matt Kenworthy, and also Christian Ginsky at Galloway, and we kind of all put out press releases, and then it kind of went out in that press release ecosystem, and some did better than others, but anyways, this picture has propagated, so yeah, I think it's kind of cool, and again, just sort of for fun. Like, this is just a cartoon, it's not serious. I'm just like kind of my idea of what's going on. Like, this planet's obviously accreting at H alpha, so you're probably seeing accretion streamers falling on it. And this one's also got a situation where it's more embedded in dust. And that's sort of the way that I'm thinking. Now, CC1 is still a little extended because you're seeing there's some significant dust here. And it's probably basically extincting the H alpha. And so this is a much less cleared object. Our line of sight's going through a lot of dust, so it's harder to see the H alpha, but we can see the thermal at least being released by the planet as at L prime. So that's why it's mostly an L prime object, whereas this object's an H alpha object. This is my thought. All right, and then there's just a couple of other things I want to just point out. It's like, hey, we're astronomers. Once we have like 4 of something, that's like a whole new class. So if you have 4 things, then you start to compare them, right? And it kind of gets exciting. And so here's like accretion rates for all the known H alpha protoplanets. And, so we've, as a function of time, so we basically have PDS 70C here, and then B here. And then we have John Lynn's object, Maxprotoplanets 1b in green. And then we WISPIT 2b here in blue. And I've kind of played it a little bit around with the scale here so that you can separate the images and see them. These are actually only taken 2 nights apart. But you can see that, interestingly enough, all of these planets tend to be a few Jupiters in mass. They all tend to be accreting actually at kind of a low rate. These are pretty low accretion rates. These are only growing by like 0.1% of their mass a year per, sort of, mega year. And so they're basically right at the end. My theory initially was that these should be really bright at H alpha because, they're accreting Jupiters of mass per mega year. And so they should be like really bright. Unfortunately, that we haven't found anything quite like that yet. Most of the planets we find are quite anemic in actually their accretion rate, assuming that they're not, there's not a huge amount of dust extinction. And I don't think there actually is because we found quite a few of them. Now, granted, all of these are about 5 mega years old. So in a way, what I'm really just sort of saying is that at 5 mega years of age, things have slowed down and we've pretty much finished the planet building process because we're starting to run out of gas. And these planets have more or less reached, the end of their growth spurt, right? And so, they're like 18-year-olds at that point. And so they're not really, they're not really changing too much.
So yeah, it is known that within 1 million years already, the most of the mass has been accreted.
So that's right.
You want to go to 1 million year old, 2 million to 2 million year old objects.
Yeah, so what Serena's saying is exactly right. And we've been looking, obviously, at some younger systems, but I think what's getting in the way is dust. I think the problem is that just like you're saying with CC1, I think the problem is that when they're really active, I think, and maybe this is an A, B, or B sort of situation where you're seeing these young protoplanets are wrapped up in a dust cocoon. And there's H alpha being generated, probably a lot, but you're really only being able to detect like the reprocessed light coming out, if any. And so it's a little harder, but we are going in that direction too. But these have been the superstars so far. They're really clear cases.
Yancy, could you speak up? Oh, Yancy, we can't hear you.
Oh.
Yancy, try it now. This should turn
I
up.
can't hear you, Yancy.
Yeah, maybe
In the chat.
Yes, sorry,
Yeah.
Nancy.
This stuff only happened, so I don't know what.
Okay, well, anyways, Yancy works on his question. I'm just going to go on and just mention we can get back to it, and maybe you can just ask me it. So then, okay, so they all accrete kind of the same rate. And then in terms of actual flux, like, well, how bright are they at H alpha? Oh my goodness.
This is here.
By some miracle of teleportation.
Control the lights, man. So to answer my question, I apologize.
Yeah, please do.
I was curious about if the dust is the problem. Can you go to action or bracket gamma, bracket lines and the infrared?
Such a great question. And so like the obvious answer to this is yes. And then of course people are like, oh, we can make web proposals and things like that. And it's absolutely true. Webb has looked at let's see if I get this right. Passion Beta? No, what the J-band line. Anyways, it's and they've been able to resolve PDS 70B and C, but you do lose a lot of resolution going to longer wavelengths, and those lines actually are not as strong as H alpha, and in fact, it's quite dramatically weaker. And I'm showing these like, oh, these are really easy to find, but they're actually pretty faint. Yeah. And they're pretty high contrast. So it's at least a factor of 10,000 in contrast and separations of 100 to 300 milliarc seconds. And that's pushing Webb at kind of that's a tough place for Webb to work. There has been some success there. I think Christians has a nice paper, but that was with a known system. I think finding from scratch objects. And of course, CAC, which is diffraction limited, obviously in the IR, and a huge aperture has also been trying to do some of this work, but it's been hard. And in fact, another argument is why not look at a hydrogen beta. Look at H beta and see if you can see alignment. H beta, which should be there for these objects, we just can't find it. It seems to be at least 20 times weaker.
Let's say something like the dust over here, or
Yeah. So the problem is because I mean, if you saw the H beta, then you could do the ratio and the exact, from some sort of K-SPE recombination, the exact extinction. Unfortunately, we just didn't find it, but Yifan Zhu was able to use HST to detect the planets in the UV. So the UV is actually where a lot of the actual energy is being released in these accretion streams. And based on the brightness in the UV, we could say that there's no more than 3 magnitudes of extinction. Because if there was more than that, you just wouldn't see these planets in the UV. So we have a little bit of a handle on it. But it's a really great question about there's all these other hydrogen lines. But so far, other than with the one exception of PDS70B and C with Webb, we haven't really been able to find these at any other lines. H alpha is an amazingly powerful line. And so it is, yeah. But it's a really great question, yeah.
But even like bracket alpha,
Yeah, I mean, I think that it's just pretty weak, because it's bracket alpha, and bracket's just so much weaker. Like bracket gamma, we use it a lot at K, but it's pretty weak. You really need a strong emission system. These planets are fairly weak lined. So, but I mean, these are good points. But you do run up against lambda over D. Well, yeah, no, it's similar to what you're doing. But at L band though, broad L, these things just really explode. They really pop at broad L because they really are right at the Wien peak. And then you got that broadband filter going for you. And so that's fairly powerful because they are around 1000 to 1500 Kelvin. Okay, so, I was just going to say that in terms of brightness, they're all kind of similar too. And then this is the last point that I want to make in the talk. It's just that, so this is a little bit of a complicated diagram, but it's in the latest paper, the WISPIT paper. But what it kind of just shows you is a function of inclination. We found a few of these systems. They all kind of look the same. If you just look at inclination of the disk fitting to the continuum image from ALMA, you can see that they all kind of fit in this range of 37 degrees to 52 degrees. Now, of course, before all the faculty members in the room jump on me because I'm making a conclusion from 4 objects. That's fair. We only have 4 objects, but it is interesting that they're all clustering in that same little area. And, if you just simulate it, there's a less than a 1% chance that this distribution you're seeing here. In other words, the red triangles are things that have H alpha planets. The blue circles are things that are big gaps in ALMA disks that should have H alpha planets, but we don't find the planets. And it's just sort of an interesting possible selection effect that H alpha is best viewed at certain viewing angles of the planets themselves. And you might say, well, I don't understand what you're talking about. And, to be clear, this is somewhat subjective and speculative. So, take it with a grain of salt. But, the way magnetospherical accretion works is that you basically, the charged particles flow down the flow lines and land on the planet. And there's a shock that occurs on the planetary surface. And that shock generates heat, maybe up to about 8,000 Kelvin. And here's a little illustration, again, done by my daughter, Emmeline, because she's the best artist I know. And so you can see that if you heat up the outer part of a planetary surface, you can create convection. That convection can drive large clouds, similar to like what the Shoemaker-Levy impactor did to the atmosphere of Jupiter. And it's also true that if you're the observer looking down these field lines, you can see the really hot region where the accretion is, where the line formation region is created. But if you look from a different angle, if you look outside of this wedge of viewing angles, you just see the clouds and you don't see the H alpha. So kind of the way an artist, a really like a professional artist at Caltech IPAC, Robert Hurt, this is what he was able to sort of envision it would kind of look like that you can kind of imagine if you do have some clouds being billowed up by the high heat being caused by the line formation region, you would actually only have certain angles that you could see your planet at, where you could see where you'd have direct access to the bright H alpha. In other words, if you look pole down, what would happen is those clouds would basically hide the really hot stuff deep down inside. You'd have a hard time seeing deep into the planet if you're looking at it from the top of the planet or directly to the side of the planet. And so there's just this, maybe there's this range of this sort of wedge of angles where you're actually able to see that H alpha region. This is somewhat speculative. The referee wanted me to take it out of the paper. I compromised and made it an appendix. So, take it as you will, but, I think maybe that's interesting and maybe it's not. And so these are just basically a summary of what I've already talked about. I'd like to stop here and just, get some questions from people if people have questions.
Thank you. Yancy, and yeah.
So on the circumplanetary disk, the scattered light looked like it was offset from where the H alpha was. Is that because there's a big gap? What's the geometric reason?
Yeah.
Cleared out a gap, or-
Yeah, so what Yancey's talking about, and here's probably my best. I went through this kind of quickly. So where I have the letter B, all right, is where the planet is. And then this is the sort of scattered light that I'm seeing around the ring. And there's a lot of asymmetries here. I mean, the biggest reason is that it's the front surface of the ring dust that's going to be lit up because it's being lit up by the star, right? And so that's going to light up the front part. And then, but you're talking about the asymmetry with the planet. And the asymmetry with the planet, I think, can be understood because it's a flared disk that's inclined. And so you'd actually expect, maybe I don't have a really good picture of it. This sort of maybe shows it too here a little bit, is that when you have a flared inclined disk, basically you're going to see the structures float a little bit away from the planet on the other side, even if the illuminated source is an external one.
It's huge, though. 9 AU across. You're talking about.
Yeah, so it's 9 AU across, but the Hill sphere for this is PDS 70b, so it's about 5 Jupiters. So the Hill sphere mapped out here is on the order of about 9 AU in total size. So it's a little bit it's of that order. It is big, but it's not outrageous. We probably would have thought maybe more like 6. But it's still there seem to be these structures. Now, to be clear, it's not exactly surprising that there's dust around accreting planets. If you can see the H alpha from the planet, there's probably a reservoir of dust and gas. So it's just a question of how big it is. Now, I'm not saying that this is stable dust. This dust could be super unstable because it's right near the Hill sphere. So half the time this dust is floating off into the star. Half the time the dust is falling onto the planet. It's really maybe just a sort of a temporary holding place for material, because there's all this dust flowing in through the gap, and it's just sort of flowing around the planet, but only temporarily, maybe one orbit, and then it falls into the star. So that whole Hill sphere will kind of get lit up by dust. It's not stable, I suspect, but it does get filled in, if you will.
So I have a question about WISPIT CC1. So your interpretation that you're not getting H alpha because it's obscured by dust, but then why don't you get any perhaps reflected H alpha from the star?
Oh yeah. Well, I mean, you mean off the dust disk or something? Yeah. So I think at some level there probably is some reflected light there, and that might actually be driving its it's really quite bright at Z prime. So that might be answering that question. If you take a broad filter, because this is a narrow filter, you take a broad filter at a bit of a longer wavelength, but I think the broad filter is really what helps instead of a narrow filter, then you can actually start to see some of that scattered light. And you can see that it's elongated too. I mean, So that's also kind of like, I'm calling it out as a planet, but that should be a point source, but this is clearly elongated. The little green ellipse shows what a CPD around that planet that has the size of a Hill sphere should be, okay? And you can see that it's smaller than the Hill sphere, but it's not crazily incompatible with being slightly smaller and elongated in a similar way.
Follow up to that, it is obscured of dust. Is there any idea as to why there's dust around that planet that's forming and not around WISPIT 2b?
Oh,
Maybe
such a good question. Such a good question. So, right. So what you're literally asking is like, well, shouldn't I see some scattered light here? Right? I don't see anything. So clearly, but here's the beautiful thing about that, and it's one line in my paper, is that the difference is, and this is an important difference, is that, well, okay, this is maybe a good example, is that the difference is that this guy, CC1, is being directly illuminated by the star, but WISPIT 2b is, has this huge ring of dust and gas between it and the star. So that's going to cast a shadow. And that shadow is probably really going to suppress the scattered light. It doesn't mean the dust isn't there around WISPIT 2b, but it's in shadow. And so it's going to be pretty weak emission. There's probably something there, but it's probably very hard to detect. And it might be the I don't think you can really convince yourself there's anything there, but that's what 300,000 times fainter looks like. You know, it's just like, you know, so we might be seeing a little bit of scattered light from whatever light can pierce the shadow, you know. It's a little bit but I think the shadowing from that bright inner ring is really wreaking havoc with our ability to see scattered light out there. Thanks.
Okay, any other question? Well, Renu here said, very cool, congratulations, Laird. There was a comment from Renu.
Oh, well, thanks, Renu.
If there is
Yeah,
any-
sure. Laird, I have a quick follow-up on this last comment.
Okay.
Your idea of shadowing the planetary disk. You know, from that, if that's correct, you can make some estimates of the coplanarity of the two objects.
Right, yeah.
Again,
So yeah, no. So we have a little bit of orbital data from the sphere data over the last 3 years. And I should have maybe mentioned this, but this guy, what we're talking about, WISPIT 2b, is orbiting clockwise. And the motion, although, well, it's not a background star. Okay, that's good. It's, you know, and its orbital motion suggests that it is consistent with being coplanar with the star. And we're just assuming, perhaps incorrectly, that it is in fact a coplanar orbit. But it does appear with the very small, we've only, you know, we had to go back to older images and sort of dig it out. And we can kind of make an argument that it is rotating clockwise and is coplanar, at least consistent with it. But you're absolutely right. We can use that. We're sort of hoping that the whole system's coplanar because it's got such beautiful rings. But you know, it's a dangerous assumption because nature's always doing weird things. So
the disk could be.
Yeah, there could be tilts and
Yeah.
warps, and you know, it could easily be the case.
Yeah, I guess, exactly what I was gonna ask about. Is there any evidence that maybe CC1 is the edge of an inner warped disk that you're seeing scattering?
Yeah. So in the paper, I'm very careful with CC1 because again, it doesn't, Gabe and I have gone back around on this a little bit, but it's not 100% obvious it's a point source. It looks pretty much like a point source at L band, but maybe it's slightly extended. It looks kind of extended, even by your eye right here, it looks a little extended. So it could be, I mean, I think there's some component of dust that's showing some resolved structure. And then there's the question is what's inside that dust? What's holding that dust there? Is it the gravity from a 9 Jupiter mass planet? Or is it some strange ring structure? And I think that's going to be really exciting to see how that actually resolves.
So we see this a lot with young objects where the inner discs are just really
So
strongly
nice,
warped. It's just so common, like
Mhm.
over and over again.
I know.
Is there almond data?
No, no. So this whole thing was discovered
Yeah.
completely independently of ALMA. Now, I would imagine that there are people that are, I'm not, but, you know, on our team, we also, you know, are pushing in different directions, using the VLT as well. And we've been following up with LBT, but I can't really speak too much about all of that. But I'm not actually involved with any ALMA. There's so many great ALMA people out there that I'm sure they've pointed, or they will soon point ALMA to WISPIT 2B. And that'll help. But I think the ring system is going to be extraordinary. It's already extraordinary in scattered light. So that's usually a really promising sign for what it'll look like to ALMA.
Really would love to see streamers going that way.
Oh, I know. I agree with that. It seems to be difficult. It might be something to do with the fact that these have almost stopped accreting. So for those streamers to be really easily detected by ALMA, that stage is passed, and we're in a very low accretion period now. So, you know, I think that's interesting. So, but anyways, I think what's exciting about it is nature is still making amazing things around stars that no one's ever looked at. And, you know, so there's amazing things out there still to be discovered. And sometimes we don't remind ourselves of that enough. But I think that this is a good, WISPIT 2B is proven to be a fascinating object.
Okay, the very last is already past time, but Jehan raised hands. So Jehan, could you unmute?
Yeah, thank you, and sorry it's over for yeah, thank you very much for the talk. I read the paper, but it's always good to hear what the author talks about. So going back to whether it's in coplanar orbit or not, and the angle that we are looking at all these four systems, right? The assumption is that, well, the rotation axis of the planet and the orbital plane, they are, rotational
Aligned.
axis of the orbital plane, they are parallel to each other, right? So that we have
Correct.
45 each angle, and then we look at the right angle. But if it's not, right, for whatever reason, planet's orbital axis is not aligned with the rotational axis, that doesn't hold anymore. So, and it is possible if, for example, planets form through gravitational instability, very violent process, right? There are simulations showing that it's possible. So I was wondering if one can use, I don't know, it's H-alpha line profile or anything else to perhaps say something about whether the planet's rotational axis is aligned or whatever.
Yeah. Maybe. I mean, to be clear, my understanding is we've never actually resolved, I mean, with the exception of maybe a paper that just recently appeared, but I don't want to comment on that. Yes, I think in theory, maybe that's possible, but that's a very difficult observation because you only get one H-alpha photon per pixel per minute.
Yeah.
So that's how faint these things are.
Yeah.
And so then to do a nice line profile at a good resolution with a spectrograph of the planet is hard. But I agree with your comment that I am assuming that the angular momentum spin vector is the same for the star as the planet, as the ALMA disk. So I'm assuming, and these are fairly young systems, so we're kind of hoping that that's the case. You know, I mean, I think nature shows us that weird things happen, like Uranus is tipped over on its side and things like that. So, I mean, I think as things get older, it can fall apart. But yes, you're quite right. That's an assumption, but well, at least I can't right now think of a really easy way with today's instrumentation. Now, maybe this is an ELT scale project that you're talking about. Maybe that could do it with an IFU, but they don't have a visible. Unfortunately, the ELT can't make diffraction limited images at H-alpha. So that's one of the things it can't do. But GMT with GMagAO-X should be able to do that. Yeah, it's put a little plug in there. It's too bad you'll miss that.
Yeah, one last thing in 10 seconds, because of the question. So We got ALMA DDT time and got continuum data on the system. Stefano Facchini is the PI.
Ah.
Yeah, so yeah, data is there now. Yeah, so we will have to look at it and analyze it.
All right, well, as soon as
Video.
yeah, as soon as it hits the Astro PH, send me an email.
Yeah, I will. Thank you. Thank you again.
Thank you.
All right.
Thank you, Jehan, for sharing
Thanks.
that. Okay, everyone, thank you very much. And thank you, Laird.